Fire. It's everywhere, right? From a tiny birthday candle to a huge campfire. It's completely mesmerizing. But have you ever actually stopped and wondered what a flame is? Like what's chemically going on inside that little flicker of light and heat? Well, today, we're going to dive right in and unpack the science behind one of humanity's oldest and most important discoveries. You've probably seen this classic experiment, maybe even done it yourself. You light a candle, pop a glass jar over it, wait a few seconds, and poof, the flame just vanishes. It's so simple, but it shows us the #1 rule of fire. It has to have something from the air to survive. It literally needs to breathe. So that's the big question, isn't it? What exactly is it breathing? What's it pulling from the air that's so important? Is it just air in general, or is it one specific ingredient? The answer to that is the key to understanding everything about how fire works. And that special something is oxygen. You know, our atmosphere is mostly nitrogen, but that crucial 21%, that's oxygen, that's what a flame is desperately gasping for. Without it, a fire just can't exist. Simple as that. This whole process has a scientific name: combustion. And all it really means is that a fuel is rapidly combining with oxygen, and that reaction releases the light and heat that we see and feel as fire. So here's the key idea. Fire isn't a thing. You can't hold it. It's an event, a really fast chemical event. And to make this event happen, you need a very specific recipe. It's kind of like baking a cake, you know? If you leave out the flour or the eggs, you're not going to get a cake. With fire, if you miss one of the key ingredients, you get, well, nothing. And that recipe has 3 essential parts. You might have heard it called the fire triangle. You absolutely need a fuel to burn, you need oxygen for it to react with, and you need enough heat to get the whole party started. So first up is the fuel. This is just the stuff that's actually getting burned up in the reaction. It could be a solid, like the wood in a campfire, a liquid, like the wax in our candle example, or even a gas, like what comes out of your stovetop. Second, our star ingredient from the air, oxygen. This gas is what we call the oxidizer, and it's super eager to combine with that fuel and release a whole bunch of energy. And finally, heat. I mean, you can have a log and plenty of oxygen sitting around all day and nothing happens, right? You need that initial spark of energy. Every single material has its own unique ignition point. That's the minimum temperature it needs to hit before it will burst into flame. Okay, now this slide is so cool because it shows just how much oxygen matters. On the left, you've got some steel wool, just kind of smoldering in normal air. But look at the right. When you put it in pure oxygen, whoosh, it burns incredibly fast and bright. More oxygen means a much faster reaction. That's actually the whole principle behind a welder's torch. Okay, so fuel, oxygen, and a heat source. Got it. But what if I told you that sometimes a fire can provide its own heat source? What if a fire could just start by itself, with no spark at all? This actually happened in Upper Egypt. A big pile of hay suddenly burst into flames with no obvious cause. Some of the locals were convinced it had to be ghosts, and I mean, you can see why they'd think that. But science has an explanation that's, frankly, even cooler. It's a phenomenon called spontaneous combustion. And what it proves is that sometimes a chemical reaction can generate its own heat. It can literally heat itself up until it hits its own ignition point. In the case of that hay, it was bacteria decomposing inside the pile, slowly building up heat until, poof, it was hot enough to ignite. We can actually see this happen right in the lab. When you mix glycerin with potassium permanganate, they start reacting right away. It's what's called an exothermic reaction, which just means it releases heat. And it releases so much heat so fast that it hits its own ignition point and just erupts into this amazing purple flame. No match needed. So knowing the recipe for how a fire starts is also the secret to how you stop one. If that fire triangle is what creates a fire, then breaking that triangle is how you extinguish it. So how does this work in the real world? It's pretty straightforward. To kill a fire, you just have to take away one of the 3 things it desperately needs to survive. It's heat, it's oxygen, or it's fuel. You remove any one side of that triangle and the whole thing comes crashing down. The fire goes out. And that gives us our 3 main ways to fight a fire. You can pour water on it to cool it down below its ignition point. That's removing the heat side. You can smother it with a fire blanket or a CO2 extinguisher to cut off its air supply. That's removing the oxygen side. Or if it's a gas fire, you can just turn off the valve, which removes the fuel side. All right, we've gone over how fire starts and how it stops. But now it's time for the big reveal. It turns out that burning, combustion, isn't some unique magical thing. Nope, it's just a really fast, really obvious version of one of the most common chemical reactions on the entire planet.
Welcome to the world of oxidation and redox, or what chemists call redox for short. A redox reaction is really just about trading electrons. One substance loses electrons. We call that oxidation. Another substance gains them, and that's reduction. They're two sides of the same coin. You literally cannot have one without the other.
So the things involved get special names. The substance that gives the oxygen is called the oxidizing agent. For our fire, that's oxygen itself. And the substance that takes the oxygen is the reducing agent, and that's our fuel. So here it is. This is the main point. What we call burning is simply a redox reaction that's happening so incredibly fast that it releases a massive amount of energy as heat and light. Fire is just rapid-fire oxidation. And once you know this, you see it everywhere. Think about it. Why does vacuum sealing keep food fresh? Because you're removing the oxygen. You're slowing down the exact same redox reactions that cause food to spoil. Rusting metal? Spoiling food? They're both just really, really slow fires.
Which leaves us with one last, kind of mind-bending thought to chew on. If a roaring fire, a chunk of rusting iron, and an apple turning brown are all just different speeds of the very same chemical reaction, what other slow, invisible fires are shaping the world around us right now?